Welcome back. In the last video I did a few problems. So today we'll continue this problem session and I want to do a couple of very important exercises in field theory that will be constantly used in the later part of this course on Galois theory. So the first one is a fairly simple statement that you may have seen in you would have seen in a field theory course. So let me just recall this. Let F be a field and let K and L be two extension fields of F. Okay, so suppose alpha in K is algebraic over F. Let sigma from K to L be a P and F homomorphism of fields. Okay, so the situation is this. So you have K and L are two extensions of F. Alpha is in K, it is algebraic over F. I am not saying K is algebraic over F because that's not required for this. I am only going to use the fact that this particular element alpha is algebraic over F and sigma is a F homomorphism. Every time I draw a picture like this, it is understood that sigma is an F homomorphism. So then show that two things. Sigma of alpha, which is in L, is algebraic over F, and the irreducible, it is algebraic, so we can talk about irreducible polynomial of sigma of L of F over sigma of alpha over F is the same as irreducible polynomial alpha over F. Okay, so as I said, this is a very standard result and it's very easy to prove this, but I thought I will mention this because it comes up in the next problem, which will be of much more importance for us. So this is clear. In fact, we will do second part first and then everything will follow. So let's say F is the irreducible polynomial of alpha over F. Okay, so this is the situation. So I claim that and let sigma of alpha be beta. Okay, so for simplicity I am going to call that beta. So we will show, then the problem is solved, right? Because it will obviously prove that it is algebraic because beta is the root of a polynomial over capital F and F is irreducible, so it must be the irreducible polynomial. So this is that's all there is to it. So let's say Fx equals an xn, an minus 1 xn minus 1 a1x plus a0. So here remember ai's are in capital F because this is a polynomial over capital F. Now what is F beta? F beta is an beta an minus 1 beta n minus 1 a1 beta a0. But this, by using the fact that beta is sigma alpha n, remember if sigma alpha is beta, sigma alpha whole square is sigma, so that is beta square, right? So that is sigma alpha square. So that's what I am going to use. But this is actually because, so now the other important thing, so this is the important point. Important point is sigma of ai is ai for all I, since sigma is an F homomorphism. Okay, so this whole thing will not be true if sigma is not an F homomorphism. So I am going to crucially use that fact. So that allows me to write this as sigma an. So I'll skip some of these things. I am not changing anything here because sigma an is same as an, so that I am allowed to do. So now using the fact that sigma is a homomorphism, I can pull sigma out all the way So that means sigma of a n alpha n plus dot 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 a1 alpha plus a0, but that is 0, right? So this part is because right, so that is just f alpha. So f alpha is 0 because f is the irreducible polynomial of alpha over f. So that means f beta is 0 and we are done. Okay, so that is the proof that if you have a field homomorphism, an element can go to a field homomorphism over a base field, an element can go to other roots of its irreducible polynomial. So this is an extremely important, this is a very easy but very important restriction on the images of an algebraic element under a f isomorphism. Okay, so just to illustrate this, so if you have very quickly I'll do this, q square root 2 over q, and you consider this. So in our situation, I'll take this to be k, I'll take this to be l, and I take this to be f, right? So this is the situation. KL are any extensions, and I am thinking of this as a Q homomorphism. Okay, so this, so we know that sigma of root 2 is must be either root 2 or minus root 2. Okay, so because irreducible polynomial of root 2 is x square minus 2, which has only 2 roots. So this is the simplest example where you can see that root 2 cannot go to anything else. This you can directly prove, of course, but this general statement here allows you to conceptually visualize this. So this tells me that root 2 can go to other roots of its irreducible polynomial, of which there are only 2. So root 2 or minus root 2. And now you can apply this problem to any situation. You can take, so if alpha is a root of this, I am just randomly writing an example. So and sigma alpha, where sigma is some k to c, alpha is here, must be one of the 3 roots of f. Okay, this is a very powerful restriction, as I said, for algebraic elements. And one immediate application of this I'll do, and this is going to be very important statement for us, is the following. Let k over f, and I wanted to also, after this I'll write one more exercise, and that will stop the video after that. So let k over f be an algebraic extension. Now I'm taking an algebraic extension. Let sigma from k to k itself, it's very important that I have k to k here, be an f homomorphism. Then sigma is in fact an isomorphism. I want to prove this. Solution. So remember, it is an f homomorphism, it takes k to k. Already we have sigma is an f homomorphism. So of course sigma is an f isomorphism is the statement. That is, an f homomorphism is given, it is injective is given. So only remains to check sigma is surjective, right? Because it takes k to k. It is a homomorphism, it is injective. Only missing point for a isomorphism of fields is surjectivity. So let us take an arbitrary element and show that it is in the image. So let alpha be in K. So you have alpha here. So let us now consider the irreducible polynomial of alpha over f. Recall that k over f is an algebraic extension. So every element of k is algebraic over f. So I can ask for its irreducible polynomial. Let f be the irreducible polynomial of alpha over f. Let alpha equals alpha 1, alpha 2, alpha n be the set of all roots of f in K. Note that f may not split in K. We are not given any such assumption. All we know is that K over f is an algebraic extension. So it will have some roots, may not be all roots of f in an arbitrary splitting field. But I don't care about that. I will take all the roots. We know there is one root at least because alpha is there. Let's take all the roots. It's a finite set. That much we know because f is a specific polynomial, its roots will be finitely many. So let's call this set A. So A is the set of roots of small f in capital K. Now I claim that f of alpha I is equal to alpha j for all I. This is by the previous exercise. Right, that is the point. So image of alpha I must be another root of the irreducible polynomial, namely f, but the only roots of the irreducible polynomial are these. So this is immediate consequence of the previous exercise. Okay, so now that means, so we can restrict f to A. So f, remember, is a function from K to K. A is a small subset. K is an infinite field potentially, right? So A is a finite set. In general, f of A could be some other set in K, but we just showed that this implies basically that f of A is contained in A, right? Because you take an element of A, apply f to it, you land again in A. So f can be restricted to A to give a map from A to A. Now look at, I'll call the restriction also f or f sub A. So it is a restriction of f to only A. It is injective because f is, right? So f is a set theoretic injection. So two distinct elements in capital K go to two distinct elements in capital K. So two distinct elements in capital A obviously go to two distinct elements in capital A. But FA is an injective map from a finite set to itself. So FA must be surjective. Right, so this is a trivial statement. So you have a finite set with 4 elements and you are considering maps from that element, that set to itself, but you also know that it is injective. So this goes to this, maybe this goes to this, this goes to this, this goes to this. So there is no way that it fails to be surjective. So it has to be surjective. That is, there exists alpha I in A such that f of alpha I is alpha 1, which is alpha, because alpha is one of them, right? So maybe alpha is this, so this must map to alpha. So alpha is in the image of K itself, so that means f is onto, right? So onto, remember, equals surjective. Surjective is a synonym for onto. So that means f is an onto function, which is exactly what we needed to prove. So this completes the solution. So this is going to be a very, very important statement for us, namely that if you have an algebraic extension and you are looking at maps from K to K, this is very important for us, then it is an isomorphism. Okay, so if K, this K is different from this K, then we can't say any statement like this. Okay, so that is the statement I want to show, that if you know that you have an algebraic extension and a homomorphism from it to itself, then it must be an isomorphism. Okay, so for example, if you take cube root of 2 zeta 3 or omega as it's called, so this is the splitting field of over Q. Okay, so this is K. So any map you take, it must be an isomorphism. But if you take to C, okay, so let me not get into this. So this is all I am saying. So, okay, on the other hand, if you take Q adjoint cube root of 2, you can take cube root of 2 times omega. Okay, so omega is a primitive third root of unity. Okay, that must be an isomorphism. So cube root of 2 times omega, that's another root of the irreducible polynomial of cube root of 2. So this is a valid map. So here K is this and L is this. Okay, so it is an isomorphism, but it's from K to L. Okay, so I may have confused you a little bit, but I just want to emphasize that you can have different fields. So for example, yeah, so maybe I could have just taken C here. Okay, so then I'll send cube root of 2 to cube root of 2 omega. So it is an algebraic extension, but it is, so, or I can take some big field. So K adjoined cube root of K adjoined cube root of 2 omega comma omega, or Q adjoint cube root of 2 comma omega. So here L is algebraic over Q, K is algebraic over Q, but this is not an isomorphism, is not surjective rather. So L is not K, so that is why it fails. So here it's very important that I have same field. Okay, so same field. Then you have a surjective map. Otherwise, you have an isomorphism, but onto something smaller than L potentially. Okay, so that's all I'm emphasizing here. Okay, so now let me just give some terminology and stop this video. So if you have an element, so K over F is an algebraic extension, rather field extension, alpha is algebraic over F, and let's say F is the irreducible polynomial of alpha over F. Roots of F are called conjugates of alpha. Okay, so this is the terminology. Conjugates of alpha are the roots of its irreducible polynomial. So alpha is a conjugate of itself, and other roots are called other conjugates of alpha. So the problem here, fourth problem here, says that image of an algebraic element must be a conjugate of that element. Okay, so conjugates are, there are only finitely many conjugates, and they are the only possible images under a field F homomorphism. Finitely many conjugates for an algebraic element. Okay, so let me just write one more exercise because I meant to do this. I won't give you the details now because I'm running out of time. So I'll just want to give you a quick, very sketchy argument and ask you to finish it. So let F be a field. The prime field of F is defined as follows. So you consider the unique ring homomorphism from Z to F. There is always a unique ring homomorphism from Z to any field or any ring, in fact, commutative ring with unity. So take that. Let I be the kernel of phi. So we know I is 0, in which case Q is contained in F, right? Because Z is then a subring of F. F is a field, so Z will and Z is contained in it, so all ratios of integers will be contained in it, so Q is in F. Otherwise, I is Pz, P prime, in which case Z mod Pz is contained in F. right? So any field will contain either Q or Z naught Pz for a prime P. So the prime field of F here is Q in this case, and prime field of F is Z naught Pz. So as you can easily see, this is all easy. I am not yet writing the exercise. So basically what I am saying is that characteristic of F is 0 implies prime field of F is Q. If characteristic of F is P, prime field of F is Z mod Pz. Okay, so now let K and L be two fields of same characteristic, and let F be their prime field. Okay, so remember, prime field is, think of it as the base for any field. So every field of characteristic 0 sits above Q. So Q is all the way down, all fields of characteristic 0 are above Q. Similarly, if F is a field of characteristic 2, it lives above Z mod 2Z, and all fields of characteristic 2 live above Z mod 2Z. So basically what we have is that all fields lie above this. Similarly, all fields Z mod Pz for all primes. Okay, so now if you take two fields in any box here, that's what I am taking. K and L are here or here or here. So, and then take be a field homomorphism. Then sigma is in fact an F homomorphism. So any field homomorphism, so if F and L, K and L are two fields which are the same characteristic, and F is the prime field, so F is either Q or Z mod Pz, any sigma fixes every element in F. Okay, so this is a very easy exercise. We briefly mentioned this when characteristic is 0, but the same idea carries over in general. So this is an exercise for you. So I won't do this, but the point is 1 must go to 1. Okay, so use once 1 goes to 1, sigma 2 is 2, minus 1 is sigma minus 1 is minus 1, and so on, and generalize that to show that it fixes the prime field. Okay, so this is the these are a few exercises that I wanted to do in detail for you, so that you are more comfortable with the concepts that are recalled. So far in the course, we have really done nothing more than recalling, and next video we are going to start our study of Galois theory. Thank you.